Good morning, ladies and gentlemen. Thank you very much for the presentation, for presenting me. It's an honor to be here with you on this presentation and to show exactly what we did in our research. My name is Jakub Szczepanski, and on behalf of AMAT, Advanced Manufacturing and Automation Technology team, Donald Wang, Collard Keo, Peter Michalski, and Stephen Williams, I will give you a conceptual design. I'll present a conceptual design of an aircraft component positioning installation system. I know the time is very limited, so I'm just going to get down to the business. That's a nice intro.
That's nice business.
It is, isn't it? So to make things clear, I divide the presentation into 8 different sections. The first section is the motivation. Then I'll move on to introduction. I'll discuss robotic arm and the guidance system. Then I'll talk about moving platform, end-of-arm tooling, final assembly, conclusion, and finally the acknowledgement. So let's start. So the first thing I'm going to discuss is the motivation. So the motivation is the following. The current situation at Bombardier is to use manual operation for lifting, holding, and positioning of a slat into the wing of the airplane. This particular airplane is a Global 5000. Now, the objective of the project is to develop a conceptual design of an aircraft positioning, component positioning and installation system that will allow for one user to operate the machinery and install properly the slats into the wing. Now, the benefits of the system are the following: higher productivity, more flexibility, lower cost, as well as the elimination of the health and safety risk, which is one of the most important considerations in this case. Now, let me move on to introduction. Now, the whole process, as I just mentioned, is the installation of the wing slats. Now, first of all, we have to understand what a wing slat is. I know some of the gentlemen that are here, such as Jonathan Hack and Edward Lara, they know exactly what it is, but many of you might not. So I just want to give an explanation what the slat is. It's the front of the wing. If you look at the image on the left side, you'll see the slat and the flap at the back. Slat allows to increase the lift of an airplane. Now, in current situation, there are multiple operators that will manually lift and hold the 100-pound wing slat. Altogether, there are 8 wing slats for the Bombardier Global 5000. Now, the solution, as I mentioned before, is a robotic lifting and positioning system, also known as the RLPS. The system itself consists of robotic arm, laser tracking system, force torque sensor, guidance system, moving platform, as well as the support structure and end-of-arm tooling. Moving into the next point, which is the robotic arm and the guidance system. Robotic arm has been selected among different robotic suppliers, ranging from ABB, Fanuc, and Kawasaki. KUKA robotic arm KR100 R2500 Extra allows for smooth integration with peripheral equipment, which I'm going to discuss next. Performance within limits, high payload, which is 180 kilograms. Payload is basically how much the robot can lift. Long reach, which is almost around 100 inches from center of rotation, as well as extra controller that is already included in the price. Now, the second part of the system is the force torque sensors. Force torque sensors allows for loading with different, it allows worker to easily move large loads into mating position. I'll actually illustrate that by a video that will follow after. It's compatible with KUKA products. Sorry, I think it's too close. It's compatible with KUKA products, which allow for easy integration between the systems. Now, the last part of the robotic arm and the guidance system is the laser tracking system, which is a Leica Absolute Laser Tracker AT402 and B-Probe. The laser tracking system used to mate the parts to the wing can be integrated with the force torque sensor. It's compatible with all the KUKA products, and it's already been proven, as well as it can communicate with the wireless communication system. Now let me just show you the quick video. That's how the sensor works. I'm going to stop at this point and I'm going to move on. I believe I don't have much time left and still have a few slides to go. Now, next point is the moving platform. Now, the moving platform has been selected among different platforms from only one supplier at this point. It's a KUKA OmniMove UTV-2 E375-300. The moving platform can support a payload of 3,000 kilograms. It's supported by the 4 mechanism wheels, which can go back and forth and side to side, and I'll illustrate that on the video as well. Next point is a support structure, which is a steel structure assembled with a support plate made from aluminum. Now, this is the OmniMove, and the lifting spindles will allow it to lift the object up and move it to any direction. And if you can see, it moves back and side to side and back and forth. Two minutes? Okay. So I'm going to move on. End-of-arm tooling. Design and build. End-of-arm tooling will have 6 suction cups altogether. The suction force will be 270 newtons. 1620 newtons, which is equivalent to 364 pounds. Now, final assembly in the robotic concept. Now, there are 3 solutions that have been proposed. The first one is the manual, second one that uses laser tracker, and the third one is a semi-automatic that uses the OmniMove as well as the fully automated robotic arm. Now, these are the 3 solutions that were proposed. This is the final drawing where all the systems are presented with different dimensions. Now, conclusion. In conclusion, we have a dual utilization, which is the lifting, holding, and positioning, as well as the transfer of objects. Cost variance between solutions is based on different level of automation. In this case, more autonomous system will require more capital. The system itself ranges from 370,000 to 635. The drawback of this system is it can only be used every 3 days, which in this case the cost is pretty high. Now, the future work for the system is belly fairings panel installation, pilot tube installation, wingtip, as well as the other aircraft components for Global 7-8000 series. And the last part, which is the acknowledgement. We would like to thank the sponsor, which is the NSERC, as well as our partners, Jonathan Hack and Edward Lara from Bombardier Aerospace, collaborators, KUKA and Schmalz, and of course, the last and foremost is our Applied Research and Innovation Center. Thank you very much. Any questions?
So we've got about 5 minutes for questions. Any questions for Jakub?
I do.
Thank you, Jakub. And you had to move so quickly through that, but I also wanted folks to have an opportunity to ask some questions. My question is what is the learning here that was made that had impact on students, and how are you going to take that learning to the next place in the next project?
So the first learning was suction cups. We haven't used suction cups at our institution. So we contacted Schmalz, and there's going to be a future collaboration between Schmalz suction cups and end-of-run tooling with Centennial. Second thing is KUKA Robotics. We're not an official partner of KUKA Robotics, but after collaboration with these projects, we have more, I'd say, insight into their technology.
Any other questions?
And I think I forgot, it's the last part is the Bombardier Aerospace. I think the most important was the collaboration with Bombardier Aerospace, which allowed us to understand more the inside of one of the leading aircraft manufacturers.
It's just a very small question.
Sure.
Gabriela, hi. Just wanting to know, it was very interesting, you said it can only work every 3 days. And
yes.
Is this something that can be improved, or what is
the
reason?
That's the thing, that's our future work, if I go back. Since the slat installation takes place every 3 days, we would like to improve or maybe upgrade the system to have it ready for belly fairing panels, as well as the pilot tube installation, wing tip installation, and other aircraft components.
Deepak?
That was a wonderful presentation, Jakub. My question is around, aerospace being such relatively low volume manufacturing. Was it easy to find technology that could be adapted in terms of automation and productivity gains for manufacturing that might be low volume, high mix?
I'll answer this from one of my colleagues' point of view, who currently works at Boeing Aerospace. They're introducing more automation into their assembly because they believe that automation will be the future. Now, since most of their operations assembly is manual, they want to move away from it. And this project shows there is a great opportunity to move away from the manual process.
Question over here.
Sure.
Was it a significant safety risk on doing it manually?
Yes, there is a significant safety risk. Imagine 3 operators lifting 100 pounds apart and positioning right at the wing. And according to the operators themselves, it's not really pleasant, and they have a lot of health issues with that. And if you don't believe me, you can ask you can ask Bombardier, they're here. They'll let you know, they tell you.
You'll see a video later on.
Yeah.
Okay, we have time for one more question.
How did the project get started? Did Bombardier contact?
Of course, it was Edward Lara and Jonathan Hack. They were the first one to contact Centennial College, and they choose us as a college of choice in terms of this project.
So they had this difficulty and they wanted to...
Yes, that's sort of an answer to the issue that they currently have.
Okay, thank you.
Yeah.
Thank you, Jakub, for your presentation.
Thank you very much. Thank you.